Okay, hello everyone. Welcome to our Monday seminar. It's a great pleasure to have with us Dorota Grabovska, who will tell us about quantum technology and particle physics. Dorota, please, you have the floor.
Awesome. Well, thank you so much for the invitation to give this seminar. As we were sort of talking earlier, this has been about a year and a half in the making. This was one of the first things that I had canceled due to COVID. So I'm excited to be finally giving this talk, though I of course wish that we could have done it in person, maybe in the future. So today I want to talk to you about sort of recent work that I've been involved in on this sort of exciting new direction of applying quantum technology to problems in particle physics. So just to give you a sense of sort of where we'll be going, because the title itself is pretty general. So I kind of want to give everyone a sense of which direction we're going to be going. So first, I'll give a brief introduction to quantum computing. And this is sort of really supposed to be quite general. So really, what are the sort of guiding principles behind quantum computing? And also, how is it implemented in practice? And particularly, what are some of the real world hardware that we now have access to? The second part of my talk will be sort of really thinking far future. And that's this question of how to simulate the standard model and beyond. So I'm going to be talking a bit about the sort of difficulties that we will be facing in sort of doing this, specifically about the difficulties with constructing Hamiltonian formulations of gauge theories. And then with that, I'll give an example of a new U1 formulation that Mia and a collaborator have recently come up with. And then lastly, I'll spend a few slides thinking about sort of more near future applications, which is using quantum machine learning for Monte Carlo event generation. And I will say that there are a lot of really interesting examples of quantum technology utilized for sensing and metrology, but I unfortunately will not have time to talk about this during this seminar. Good. So with that outline, I also want to highlight sort of the main take-home messages so you kind of know what to be keeping an eye out for. So in this talk, I try and highlight 4 main points. The first is that quantum computing has the potential to probe theories that we currently can't access via classical methods. And I do want to highlight that this is a potential, not a guarantee. But if it pans out, it's really exciting because it really gives us a way to look at things that can't be looked at in other ways. The second is that even with this sort of far future work or far future goals, the time to start setting down the foundations is right now. We don't have to wait for the technology to be ready. We can start working on very interesting problems right now. However, there are also interesting particle physics problems that we can now apply quantum computing technology to. So despite the fact that we are in this so-called noisy intermediate scale quantum era, there are problems that we can probe on these sort of smaller noisy machines. And I'll give an example of that. And then lastly, I guess sort of the overarching theme is really dream big, but also be realistic. And so with that, all of this sort of hinges on the sort of recent developments of really existing quantum hardware. The fact that we now have real world quantum computers that people can access. So on this slide, I sort of show a couple examples of different quantum hardware. Starting on the left, this is quantum hardware that uses superconducting qubits. So this is commercial quantum computing. The 2 that I show is IBM-Q here on the very far left and Rigetti. And I do want to highlight that IBM-Q is really awesome in terms of starting out quantum computing adventures because they give everyone open access to small quantum machines via cloud computing. Additionally, CERN has an agreement with IBM-Q that allows us to run on their larger machines. So if you have some problems that you are interested in looking at, it is possible that we could collaborate and get you access onto those larger machines. Moving on to a different type of technology is trapped ion machines. So instead of using superconducting qubits, these machines use trapped ions to sort of get the qubits. And 2 examples of companies working on that is Honeywell's here on the far left, and then IonQ on the right or in the middle. And again, IonQ also allows some access to their trapped ion machines. It is not open access, but there are grants that you can apply for. Above this, there's a different type of quantum computing. This is the D-Wave, which is a quantum annealer. This works on a sort of different architecture and also a different way of thinking about how quantum computing works. And then lastly, I did want to highlight that there are actually even academic quantum computers. So this is an example of an academic tabletop quantum computer utilizing cold atom technology. Okay, so with that showing of existing quantum computers, we should actually talk about what is quantum computing. So the general idea of quantum computing is to utilize the collective properties of quantum states to perform calculations. And what I mean by collective properties are things like superposition or interference or entanglement, things that are truly quantum, and figuring out really how to use them so that we can do calculations. And the expectation and the hope here is that we might see a dramatic improvement in runtime scaling simply because of this sort of collective nature. And really the hope is that we see that improvement on problems that run exponentially slow on classical machines. So the canonical example of this is Shor's algorithm, which is a method for factoring large numbers. And the reason why a lot of people think about Shor's algorithm and give it as an example is because this factorizing of large numbers is the backbone of many encryption schemes. So if you can do it faster, it breaks encryption. So what I show here is the runtime scaling for a quantum algorithm versus a classical algorithm, showing how it scales with n, the size of the integer. So the thing to notice is in this sort of upper line, which is the quantum algorithm, that's Shor's algorithm, you see that everything scales with log n. So either log n squared or log n or even triple log n. However, the fastest classical algorithm, shown here, scales exponentially with the log of n. So this means that the larger you make your integer, the more benefit you see out of this quantum algorithm, or perhaps the more slow your classical algorithm runs. So this is one place where we sort of see this dramatic improvement in runtime scaling. And I do want to highlight the sort of interesting discovery I made when I was first starting to write this talk, is that I had always been under the assumption that the issues with like creating quantum computers or using quantum computing were more practical in nature than theoretical, that the idea of quantum computing existed and the issue was how to actually implement, physical qubits. However, it turns out I was wrong, and it wasn't until the early 80s that we even knew that quantum computing was possible. And what I mean by this is that we didn't have a quantum mechanical model of Turing machine. So the entire basis of quantum computing wasn't yet developed. And so here, just for those interested, I dropped this sort of first paper that really provided this theoretical underpinning for quantum computers. Okay, so with that, now that we actually have the theoretical underpinnings of a quantum computer, we know it can be defined in terms of a Turing machine. What kind of computing can we do? So in general, there are kind of two different types of quantum computers. There are additional types, but these are sort of the two main ones that people think about. And those are analog quantum computers and digital quantum computers. So starting with analog quantum computers, the idea behind an analog quantum computer is to use one controllable quantum system to simulate the behavior of another. And so the nice thing about this is because you're using one quantum system to sort of simulate another one, you actually have continuous time evolution of the system of interest. So you don't have to do anything about sort of discretizing time. You can just actually naturally let the system evolve as it would. And at least in our universe, time evolution is generally continuous. Most analog quantum computers are built from cold atoms on an optical lattice, appropriately tuned. And this appropriate tuning is sort of the key, I would say, downside of analog quantum computers, in that these aren't general or universal computers. So if you have a system that you want to model with an analog computer, quantum computer, you need to tune that quantum system to reflect the desired physics. And so this is not a universal way of doing a calculation. So one way that you can think about an analog quantum computer is that it's kind of like an effective field theory for a more fundamental quantum field theory, but just made physical. And of course, as we know, not all effective field theories work for all fundamental physics. You kind of have to pick the correct one. And I do want to highlight this sort of little interesting tidbit is that this idea of using physical toy models to understand more complicated systems has a long history in physics. So an example of this is in the late 1800s when Maxwell, published his Maxwell's equations. People didn't really understand how to solve those equations, and they didn't really have a lot of intuition for how things worked, and they couldn't, just calculate it because everything was with pen and paper. So what they did is they built physical systems made out of rollers, bands, strings, things like that, in order to understand Maxwell's laws and the luminiferous ether. So here I sort of show two examples of these sort of machines used to explain Maxwell's equations. Contrasting with analog quantum computers are digital quantum computers. And so here, this is a fundamentally different way of thinking about a simulation or a computer, but perhaps one that is more intuitive for us. So the general idea here is to sort of do what's done in classical computing, but just make it quantum. And what I mean by this is that you construct a set of logic gates, put that onto qubits, and then build a circuit from these qubits, from these components. So essentially, this is the way that we think about classical computing with bits and logical gates like and, or, things like that, but you just have to turn it into a quantum. And I will say not all classical gates are quantum gates, and it actually is an interesting problem how to make do with sort of a new set of logical gates. Now, because you are using a circuit backboard, you are actually sort of using a discrete way of replicating the system. You can only do discrete time evolution of the system of interest. So the same way that we have digital classical computers with discrete time evolution, this is the exact same thing on this quantum computer. So you have to actually think carefully about how to carry out this discrete time evolution. I will say that any two-level quantum system can be made into a qubit because you only really need those two levels. And the nice thing about digital quantum computers that sort of is the trade-off for having this discrete time evolution is that it's universal. And what I mean by universal here is that essentially any circuit that is properly defined and built out of quantum logic gates can run on any digital quantum computer. So as long as you can define the circuit, it will run. So the hard work is actually figuring out how to translate the physical system into the language of qubits and gates. And this is sort of where a lot of our work right now is focusing on, is actually how to take our system of interest and implement it onto qubits and gates. As an example of how one could think about doing this is using essentially the basic building blocks for abelian gauge theories. So essentially how to implement the Kogut-Susskind Hamiltonian on a quantum computer. So for the fermions, essentially you can define the basis states via the occupation number. And then the gauge bosons, you can essentially, I'm sorry, I have construction being done outside my house that I can't control, so I apologize for the background noise. So the gauge bosons, to do that, you really have to think about sort of the quantum mechanics of gauge bosons. And we know from Hamiltonian formulations that there are canonical commutation relations for gauge degrees of freedom, namely that the vector potential and the electric field essentially play the role of X and P in our sort of typical canonical commutation relations. So this really is used to define the encoding. And what Kogut and Susskind do is that they use the electric field as basis states for field excitations So they do a basis in terms of field excitations, and then the gauge links themselves act as raising operators, sort of given like this, where this gauge link is the exponential of the vector potential. And if you sort of carefully apply this canonical commutation relation with this exponentiated A, you'll naturally recover the sort of raising operator property of the gauge links. So this is one way they could think about encoding abelian gauge theories into a quantum computer. Oops. And so the nice thing about sort of both of these ways is that they can sometimes be used to simulate the same theory, but in very fundamentally different ways. So an example of this is the Lattice Schwinger model, which is essentially QED in 1+1 dimension. And for this theory, we've done both analog and digital simulations. And when I say we, I mean the community has carried out analog and digital simulations. So for the analog, people used essentially cold atoms and a trapping potential tuned to sort of reflect the correct physics. And on the digital side, it was a specially designed circuit utilizing superconducting qubits. And the key observation for this model is that you have pair production. So essentially out of a vacuum, you can pair produce an E plus E minus pair. So the nice thing is that both of these groups ran these simulations and they see this time-dependent pair production. So for both, X is running time, and then Y is the sort of expectation value of this pair production. And they essentially look relatively similar. We see this sort of oscillatory behavior in time. So essentially, in the Lattice Schwinger model, you can choose to do analog or digital simulation, and you get similar results. So with that, we can now actually start thinking about what are the quantum computational strategies for high energy physics. And with this, we really need to think carefully about which high energy physics problems are the correct ones to be looking at right now. And this really is because quantum computing is still in its infancy. And so not all problems are going to be well suited for it right now. And also perhaps not all problems are worth the large investments thinking into the sort of far future. So when I'm thinking about sort of what to apply sort of quantum computational methods to, I have two general criteria for thinking about a physical problem. And only if a problem satisfies one of these two criteria is it worth sort of applying quantum computing to. So the first criteria is whether the calculation that you want to do is exponentially hard with classical computing methods. So examples of this are things like real-time dynamics or finite density nuclear matter, or a personal favorite of mine, chiral gauge theories. These are problems that you can't apply classical Monte Carlo lattice methods to, generally because of sign problems. And that's always going to be exponentially hard. And the hope is that maybe it won't be on quantum computers. And the second is whether the problem already might see an advantage with NISQ era hardware. So one example that I know of that I'll sort of touch very briefly on is this augmentation of classically generated data sets. And I would absolutely love to find more because I think there are potentially several problems that could see an advantage even with current NISQ era hardware. But this is sort of how I think about which problems are interesting to think about from a quantum computing perspective. And in particular, sort of this workflow when thinking about these problems is really sort of what you should focus on. And so there's sort of three things that one could focus on when looking at quantum computing applications for high energy physics. And sort of thinking what is necessary to work on. So there's the sort of theoretical developments that one could focus on. These include things like how do you actually write down the Hamiltonian for a lattice gauge theory? There's algorithmic developments. How do you implement that Hamiltonian onto a quantum circuit? And then there's optimization and benchmarking. How do we make the circuit as efficient as possible given limited resources? And I will say that because quantum computing is really in its infancy, right? We don't have a lot of examples of systems to put on quantum hardware. We don't have very large quantum computers. All three of these are currently necessary and kind of have to be done simultaneously. You might write down an amazing Hamiltonian for a gauge theory and then look at it and it requires millions of qubits and has a very, very deep circuit that's just never going to run on current technology. So you really have to think about all three of these when thinking about quantum computing for particle physics. Okay, and so with that, I'll move on to sort of one of my examples of simulating lattice gauge theories on quantum hardware. But I did want to pause and see if there's any questions, especially because I can't see chat. Okay, if there's no questions, I will move on to this, which will sort of be the main rest part of my talk. Good, so since I want to think about simulating lattice gauge theories on quantum hardware, I should at least spend a very brief moment talking about how we do this on classical hardware. So essentially the main sort of field that's thinking about classical simulations of gauge theories, at least from first principles, is lattice QCD. And as we all know, lattice QCD is a highly advanced field which utilizes high performance computing and can actually carry out physical point pion mass calculations of light hadronic physics. And it has, a lot of input into sort of experimental searches now. So it's really, really well developed and really working at that physical point. The methodology for lattice QCD is essentially working with a path integral formulation, analytically continued into Euclidean spacetime. So sort of here I show this path integral formulation right here. And then as long as everything is real and positive, you can use Monte Carlo methods to sample the path integral. And of course, since we are using digital classical computers, we have to digitize everything or discretize everything. And so here on the right, I show sort of a space-time grid. This is my lattice, where fermions are implemented on the sites. And then gauge links, which are sort of my gauge degrees of freedom, are essentially linking the different sites. Now, this method works really, really well, unless you're trying to simulate things like real-time dynamics or theories where the fermion determinant is not real or positive. And the reason why that fails is because essentially now this expression right here is no longer real and positive, and you no longer have a well-defined probability for your Monte Carlo. So lattice QCD is really good at doing some things, but really struggles with others. So the hope is that we can now use a fundamentally different computational strategy, which is a digital quantum computer, to simulate theories that aren't accessible on classic ones. Now, in order to do this, we need to address two key aspects of gauge theories and how to implement them onto a digital quantum computer. The first is that gauge theories, sort of by their name, have a large degree of, have gauge invariance in them, and they have a high degree of redundancy. And so one way to sort of think about this is that the physical Hilbert space is significantly smaller than the full Hilbert space. So you can think about this as, the fact that we gauge fix, or there's sort of gauge redundancies, things like that. And so if you had to define a basis of states for this full Hilbert space, that's going to be extremely expensive if the one you're really trying to access is just this little bubble right here. So when we're thinking about how to implement gauge theory Hamiltonians onto a quantum computer, we really need to think hard about how to construct our Hamiltonian so that it is resource efficient, so that we really maximize our chances of sort of staying in this physical Hilbert space. Now, I'm sorry, saying the physical Hilbert space and also not violating things like Gauss's law, right? There are certain symmetries of the theory that really cannot be violated. The second thing that one has to think about is the fact that we are doing this on a digital quantum computer means that we need to truncate and digitize the fields. And so what I mean by this is that the Hamiltonian operators are really defined with a finite number of discrete basis states. So an example I can think about is sort of this circle in the continuum, in a continuous circle. The angle theta goes from 0 to 2 pi. And there's an infinite number of angles between 0 and 2 pi. However, if I now try and discretize the circle into a polyhedron, for example, a polygon, we see here that there are essentially 5 discrete angles that theta can take on. And so this question of how you sort of do this digitization and truncation carefully to still reflect the physics that you're trying to go after is something one really has to be careful about when sort of trying to implement a gauge Hamiltonian onto a quantum computer. So as an example of the importance of carefully choosing your digitization, let me take sort of a relatively simple example, which is the quantum harmonic oscillator, probably one of the first quantum systems we all learned to solve. So this simple toy model actually demonstrates really well the pitfalls of choosing an unwise digitization. And we'll sort of go through exactly what goes wrong. So my goal is to take a quantum harmonic oscillator where I know the exact solution and try and find the low-lying eigenstates on a digital computer. So the goal is essentially, to say it more clearly, using only 2 L+1 states, how well can I replicate the low-lying states of the quantum harmonic oscillator? And in this case, L here is an integer. So again, I write the Hamiltonian right here. This is our favorite quantum harmonic oscillator. And I'm going to choose to work in the X basis, just because that seems intuitive for me. And in this case, it's pretty trivial to digitize the X operator, mainly because it's diagonal in this basis. So I'm just going to say, okay, I'm only going to include values of X between minus X max and X max, and I'm going to digitize it evenly, just to make things simple. So this is sort of my digitization of the X operator. And the key thing to note here is that I have this additional degree of freedom, X max. That is a free parameter I will get to tune. Now, the difficulty in this sort of digitization comes out when thinking about the momentum operator. As if I'm working in the spatial basis, this operator is not diagonal, right? X and P do not commute. And so now we can start trying to think, how do we want to represent this operator in a finite matrix? Option 1 is to just use the finite difference version. We know that the momentum operator can be written as a derivative of, so why don't I just implement the derivative as a finite difference? So this is sort of my first guess about how to write P squared. Now I can implement this actually just even on a classical computer as a matrix and find its eigenvalues and compare it to the known eigenvalues of a quantum harmonic oscillator. And when I do that, we don't really do very well. So what I've shown here is on the x-axis, I show possible values of x max. On the y-axis, I show the precision and energy for the first 5 excited states. And what you'll see is that essentially, except for these very, very finely tuned points, you don't really do better than % level accuracy anywhere for any of the states. And even more so in a place where you will get really good precision on one state. For example, here, the 3rd excited state does really well. All the other states don't look great. So it's not even clear which X max you want to use. So for this option of the momentum operator, it's not clear which X max to choose, and you don't get great precision. So hopefully there is a better digitization choice. So another thing that we can do is to use the exact undigitized eigenvalues and then Fourier transform to change basis. So what I mean by this is the exact same way that I knew what sort of the eigenvalues of the X operator were in its diagonal basis. I can say I know the exact eigenvalues of the momentum operator in the sort of undigitized theory. So let me just use those and then Fourier transform that diagonal matrix to make it non-diagonal. And the reason why you choose a Fourier transform is because we know that X and P are conjugate variables. They're always related by Fourier transform. And so with this choice, the hope is that you will do much better for your energy precision. And in fact, that's exactly what we find. So this is looking at these sort of exact momentum eigenvalues, doing the same thing, scanning through X max, and then changing the precision and the energy, and looking at the precision and the energy. And there's two things to notice in this plot. The first is that your precision is significantly higher by several orders of magnitude, right? This ground state energy gets down to 10 to the minus 9, which is incredible. But even more importantly, notice that you achieve the best precision for all of these states at the exact same X max, right? These minima all line up. So not only do you have good precision, but you get good precision in all states. And so this is really sort of what you really want to do for this quantum harmonic oscillator is essentially choose this X max. And the nice thing about this is, at least for the quantum harmonic oscillator, we can exactly calculate what X max is. There's an analytic expression for it, which is given right here. And the way to think about that, to sort of get some intuition about why this is the optimal value, is by looking again at the Hamiltonian. So here I write again the quantum harmonic oscillator, where I've factored out or rescaled the mass, the frequency, all of that. And the thing to notice is that in this formulation, X and P are essentially exactly interchangeable. There's nothing differentiating momentum from space. And so here the eigenstates have the exact same width in position and in momentum space. And so you would want to digitize them in the exact same way. So if you say that delta X is equal to delta P, this is what you'll recover. And I will say the sort of really nice thing about this optimal X max is that you can actually relate it to what's called the Nyquist-Shannon sampling theorem, which essentially says how to get the best optimal fit to the undigitized theory. And I will say this is something that was looked at before. This is actually all worked out by this paper by Natalie Clow and Martin Savage, where they thought about essentially implementing this on a quantum computer. And so this is the plot that they had initially showed. And so what you'll see is this sort of minimal matching of the optimal X max continues regardless of how many qubits you use. So sort of a generic property of this digitization scheme. Okay, so with that, we have sort of seen why a wise digitization is important, even without gauge degrees of freedom. And so now we're going to move on to sort of the second issue for at least for gauge theories, is how to enforce gauge invariance and reduce gauge redundancies. So the strategy that I want to take for defining a Hamiltonian for lattice gauge theories is to really define the Hamiltonian purely in terms of physical states. And the reason why I'm doing things purely in physical states is because I don't want to have to create a basis that spans the full Hilbert space when I know my theory only really is allowed to live in a very small subsection. So this is a way of trying to get resource efficiency. Now, there's a couple ways that we can do this. The first is to enforce Gauss's law by hand at each lattice site and thus reduce redundant links. So what I mean by physical states are states that obey Gauss's law. So I give an example here. This is a two-dimensional example where I have just a 4-plaquette universe with periodic boundary conditions. And in this case, there's only 8 links. And at least some of these can be constrained by Gauss's law. And so what I mean by Gauss's law is if I, for example, look at this point right here, this 1, 1, there's 2 links coming into it. There's 2 links coming out of it. If I satisfy Gauss's law, I better not produce any charge sitting right here, because I'm working in a purely I don't have any fermions. I'm working in the Q equals 0 sector. And so what this means is that there's a relationship between the links coming into a site and the links coming out of it. This is sort of that equation right there. And I can solve it site by site. Now, this is a pretty tedious way of doing things. You can do it. And in fact, you can define a maximal tree to sort of systematically eliminate redundant links. So you have a systematic way of defining which are the redundant links, and then you can just solve, these many coupled linear equations. However, that does require that you do this site by site. And as you scale up your lattice, you have to sort of redo this, which is not an optimal way of doing things. So method 2 is working with what's called the dual basis formulation, where Gauss's law is automatically satisfied. There's a sort of simple way to think about how this dual basis formulation works, which is essentially just doing a change of basis. So instead of working with electric links shown here, I can instead define a rotor as the sum of the links going around a plaquette. Now, these are, in terms of electric fields, these aren't the plaquettes themselves. So an example here, again, focusing on my 2D example, this rotor R1 is defined as the sum of these 4 links going across. And you can, again, sort of do this for any size lattice, but it's kind of a non-generic way of doing things, right? Every time you add an additional lattice set, you have to sort of resolve these equations to get your sort of rotor basis. So the more precise way and the more generic way of doing this is to actually decompose your electric field into tangential and longitudinal components, and then rewrite your Hamiltonian in that. And the nice thing about this is that the longitudinal component of your electric field, when decomposed in this way, is related to the total charge density. So this is sort of Gauss's law encoded right here. And then your tangential ones are now going to be these rotor fields. So I will say that this sort of dual formulation has been looked at by multiple people, and it is really sort of a gauge redundancy free way of encoding a U1 gauge theory. And so this is the Hamiltonian for the Q equals 0 sector, where essentially your electric fields have changed into these rotors, and then your plaquettes are actually encoded in this magnetic operator. And I will say the Hamiltonian I show right here is for the non-compact U1, where I haven't sort of compactified the U1, but I can do the exact same thing for the compact U1 theory. And in this case, this operator just turns into a cosine. Okay, so I've talked a bit about the sort of importance of digitization. I've talked about how to think about essentially Hamiltonian formulations of lattice gauge theories. And now I want to really think about how to bring them together to write down a Hamiltonian that can be put on a quantum computer. And I will say I'm obviously not the first person thinking about this, but Christian Bauer and I, so our collaborator and I, have come up with what we think is sort of a nice way to do a U1 gauge theory. And the idea is to combine this gauge redundancy-free dual representation with the quantum harmonic oscillator digitization method. And the nice thing about this is it gives us a really precise way of encoding the undigitized theory. It's really resource efficient. And it just sort of makes intuitive sense, at least for us. So the idea here is that for step 1, we're just going to digitize the rotor and the magnetic fields, doing exactly what we did with the quantum harmonic oscillator. So here is my sort of magnetic field, here is my rotor fields, and then again, now when I write down the operators, or I define the digitized rotor operator and then the digitized magnetic operator, for the rotor operator, I have to apply this Fourier transform and inverse Fourier transform to take it into the magnetic basis, because I'm going to be working in the magnetic basis itself. Now, up to this point, we haven't talked about what Bmax should be, right? Just like in the quantum harmonic oscillator case, Bmax is a free parameter that we have to tune appropriately. Now, you might think, okay, well, what's the benefit of this? You know, if you still have to run some sort of numerical fit for Bmax, that's still a computationally hard process. But the nice thing is that based on the quantum harmonic oscillator method, we actually have an analytic expression for Bmax. So you don't have to do any sort of optimization, numerical optimization, search algorithm, things like that. You can just use our analytic expression for Bmax. And in this case, for the non-compact version, this is really just it's a coupled quantum harmonic oscillator. And so the Bmax is essentially just the quantum harmonic oscillator one, just rescaled because of some factors in front of certain terms. Now for the compact version where you have cosines of the magnetic field instead of just the magnetic field, depending on how large or small your gauge coupling is, you are either going to use the non-compact version, or if your gauge coupling gets too big, you sort of continue on into this other regime where you actually map onto the Kogut-Susskind formulation. So the nice thing about this formulation is that you can smoothly interpolate between weak coupling and strong coupling. So you don't need a different formulation for different strengths of coupling. You can just use the exact same one and you'll smoothly interpolate between the two of them. Okay, so with that, let me show you some plots that kind of hopefully demonstrate some of the things that I've been saying. So again, the idea here was to combine the gauge redundancy-free dual representation with the quantum harmonic oscillator digitization method. And so here we analyze the non-compact theory because we can actually solve this theory exactly. And there's two things to take away from these plots, and I'll sort of walk you through that. The first is that we can achieve per mil accuracy using just 7 states per site. And the second is that the canonical commutation relations are minimally violated if you choose the optimal Bmax. And the reason why we care about the canonical commutation relations is because when they're minimally violated, we get the most faithful representation, right? We've defined the theory in the sort of undigitized way. Sorry, we've defined the theory in the undigitized world based on these canonical commutation relations. So if you want to try and replicate that theory using digitized operators, you better try and reflect the you better try and represent the commutation relations as best as you can. So with that, let's actually take a look at these plots so I can sort of show you how I get these takeaway messages. So here we work with L equals 3 and L equals 4. So this is my 7 states per site and 9 states per site. The colored lines are the precision and energy. So red is ground state, green is first excited, blue is second excited. And the scale for that is here on the left-hand side. So here we see that the ground state really gets 10 to the minus 3. The dashed and dotted lines are essentially how badly the commutation relations are violated. So we see that, again, you sort of get, you know, per mil violations in it. So very small violations. And I will say that on the x-axis, what we're scanning is we're changing Bmax compared to the optimal one. So this one right here is essentially if you chose the Bmax that we recommend. So this seems to be a pretty good representation of two-dimensional U1 gauge theory without any fermions using this sort of digitization method.
Sorry, can I ask a question? So
yeah,
what happens for L equals 2? How bad is it?
So for L equals 2, it would probably be an order of magnitude, maybe less in the ground state. The higher ones start getting bad because you kind of, in some sense, almost don't have enough states for it. But yeah, I don't have the plots right here, but I think for the ground state, it's like 10 to the minus 2 precision, yep. maybe 5 times 10 to the minus 3.
So roughly by increasing L by 1, you gain an order of magnitude in the
yeah. It's definitely that there's a sort of exponential convergence that you see. Yeah, and again, so it really does depend also sort of choosing L equals 3 or 4. You would really choose it based on how many states you wanna get accurately. Because I mean, this sort of precision, I mean, you're also just going to be swamped by actual hardware noise. So yeah,
thanks.
Okay, good. But yeah, so sort of with the digitization method, we can now, let's say, this sort of works as well as we think. We know how to implement on a quantum computer, and now let's dream big and think about, well, okay, so we can do U1. What about non-abelian? What about 3 + 1 dimensional non-abelian? And so what I kind of want to highlight, is okay, we have this method for U1. So what's the feasibility of near-term QCD simulations, right? This is my dream big. So the first question to ask is, what are the quantum computing resources needed to simulate QCD? So let me say I want to do a desired simulation where I work at the physical point. So my pion mass is 140 MeV. I use this many lattice points, that 192 times 96 to the cubed. And then I have a lattice spacing that's sub-femtometer. Now, if I look at quantum hardware, my naive number of qubits is something like 3 × 10⁹. So this is a calculation you're not going to do anytime soon on quantum hardware. Additionally, if you're not doing things that have sign problems, and you look at the classical hardware simulation, assuming 100 gauge configurations, this only takes 20 million core hours. So this is a simulation that you can do, and in fact has been done. So trying to sort of take, this simple U1 model and immediately jumping towards talking about, physical point QCD simulations is not really something that we can do in this sort of NISQ era. We are very far away from doing this physical point simulations. However, that doesn't mean that what we're doing right now is not important, right? We are setting the groundwork for these sort of far future simulations. And even more importantly, at least for me, these toy models are interesting in their own right. We can look at interesting physics and lower dimensional theories without necessarily having to think about the applicability in the far future. And so, of course, for me, one of the things that I find most interesting about these approaches is that you can potentially do theories that have sign problems on quantum computers. And this includes things like chiral gauge theories, which is a topic that is very near and dear to my heart that I won't talk about here, but feel free to ask me about that later. I do also want to point out that this feasibility can change dramatically based on algorithmic advancements. So even with classical hardware, if we had asked this exact question 20 years ago, it would have taken 640 billion core hours. So 20 years ago, people were saying there's no way we can do physical point pion mass lattice QCD simulations because it's way too expensive. And then purely based on algorithmic development, not hardware, algorithm, we can now do these simulations. But again, near-term QCD simulations on quantum computers, probably not going to be a thing. Which then brings me to sort of the second part of my talk, or the last part of my talk, which is just a few slides, which is trying to figure out what we can do in the near future. I know what I want to do in the far future, but what about the near future? And so an example of this is trying to apply quantum machine learning to interesting problems in particle physics. Specifically, we're thinking about Monte Carlo event generation. So looking at the LHC, when we think about simulation of LHC events, we require a multi-step process. And each of these processes has different energy scales. And we really kind of have to step through it in order to extract useful physical observables. And so some of these steps or processes include things like the sort of hard matrix element that sort of is at the core of the scattering. There's a soft parton showering, or the parton showering of the soft radiation. There's a hadronization that happens here. There's pileup because we're also flinging billions of protons together. And then on top of all of that, there's also the detector simulation of ATLAS and CMS. And so because the LHC produces essentially 1 billion collisions per second, this is a very complex environment, and the simulation is quite computationally intensive. And so the question that myself and some collaborators had is whether quantum machine learning on NISQ era hardware could help. So what we did is we applied a trained neural network to try and augment the data produced by classical Monte Carlo event generation. So let me sort of give a brief explanation of how this works. So what we chose to work with is something called a GAN, which is a generative adversarial network. And the idea here is that two networks compete against one another. And through this competition, one network learns the underlying distribution. So to give an example of this, or an analogy of this, we can think about this as sort of what might happen between an art forger and an art historian. So the art forger is trying to create fake art that they can pass off as authentic. So that's going to be our generator. Now there's an art historian who's trying to detect this fake art to keep it from flooding the market. That's the discriminator. Now, this training is essentially, you can do a cut scene of, a high stakes film noir, cat and mouse kind of game, until eventually, if there's a successful training, the art forger will learn enough to be able to replicate paintings or replicate art that was actually real, but also create new ones in the same style. So essentially the art forger can now create new art without looking at the old art and still fool the discriminator, still fool the art historian. So what we did is we use this GAN, and what we did is we actually created a novel generator called a QGAN, where this quantum generator, so this new thing that we developed, this is purely quantum. Unfortunately, we're still having to use a classical discriminator. So we're currently using a hybrid classical quantum approach. However, even with this, we were able to run this style QGAN on real data using real quantum machines. So what I mean by this is the data that we tried to augment is real Monte Carlo generated data for the PP to TT bar process. So this is a process that happens at the LHC. And this data was generated using MadGraph. Additionally, we ran this architecture on an IBM-Q quantum machine. So IBM-Q Santiago is a 5-qubit quantum machine living somewhere in the world in some IBM lab. Now, there's a couple of things to sort of take away from this slide. So here on the very top, I show the distribution functions for the variables S, T, and the rapidity. And the thing to notice is that the data here is non-Gaussian, especially in S and T, and also correlated. So this generator had to learn highly correlated non-Gaussian data. I don't show the circuit, but it does only require 3 qubits and doesn't have a high gate count, which means it's not terribly affected by hardware noise, which is the issue in the NISQ era. And even despite the noise in the machine, we actually see successful data augmentation. And the way to see that is looking here at this bottom plots. And what we did is we looked at how essentially a ratio between the reference data and the generated data. So, for a given value of S, how many counts do we see from the generator and from the reference? And the way to see this is essentially anywhere where you see white, that's when the generator was spot on. And in fact, in these plots, we see a fair amount of white. So this was a successful data augmentation. And what I mean by this is this training was done on 10 to the 4 samples, but then we generated 10 to the 5 data samples from it. So we used a smaller data set and then increased it with this GAN. Good, and so with that, let me quickly come to sort of my conclusions. So in this talk, I tried to highlight 4 main points. The first is that quantum computing has the potential to probe theories which we currently can't access using classical methods. And for me, the sort of most interesting possible direction is the fact that we might someday be able to do real-time simulations of gauge theories on quantum hardware. So really looking at these theories that have sign problems on classical hardware. Second, that the time to really start thinking about these sort of directions is not in the far future, but right now. And there's sort of two reasons for this. The first is that, exploring lower dimensional gauge theories is scientifically valuable. There's a lot of things we can learn from looking at 2-dimensional, 3-dimensional theories. And additionally, there's a lot of active collaboration between academia and industry. So now is the time to be working with and talking with our industry cohorts. Thirdly, there are now even particle physics problems that are amenable to quantum approaches on NISQ-era hardware. So there's things that we can actually do right now, even despite the sort of noisy quantum hardware that we have. And the last is dream big, but also realistic. And as a last thing, because I know I'm essentially out of time, I do want to just spend one slide flashing this in the sort of dream big, but realistic. Is something that I've been working on for the past year and a half, is the CERN Quantum Technology Initiative, which is a CERN-wide initiative trying to figure out CERN's role in the quantum technology within Europe and beyond. And as my last slide, I'm just going to leave this up. This is sort of the 4 top-level objectives of the theory and simulation branch of CERN's Quantum Technology Initiative. This is the branch that I lead and coordinate. So if you have any questions, please feel free to either see the QTI roadmap or reach out to me. And so with that, I will say thank you and take questions.
Okay, thank you very much for this very nice talk. It was very clear.
Yeah.
So we have ample time for comments and questions from the audience. If you have any question, please feel free to ask directly. I have a quick question. Mm-hmm. So towards the end, you mentioned about the data augmentation using the quantum machine. So is this actually faster than doing everything like classically or not? So what is the advantage?
Yeah, so good. And we get this question a lot. So right now we haven't compared it to the sort of classical methods. And the reason why we haven't compared it yet is because this first paper was really a proof of concepts paper. So what we were really sort of hoping to see was whether this even works. So it's possible that, when we actually ran on real hardware, these plots would just be a complete mess, at which point we would never have to worry about doing the benchmarking because it was clear that the process just doesn't work at all. So yeah, so sort of, the applicability of this and the utility of this will really depend on how well it performs moving forward.
And Tony, yes, please ask directly. Thanks.
Thank you very much for this talk. The same thing as we were telling the first example, in which you were mentioning this quantum Hamiltonian, whether this choice that was optimal had anything to do with coherent states, because precisely coherent states of the harmonic oscillator are the ones in which you treat symmetrically the momentum and the position.
Yeah, so I would guess that is exactly right. That there is that this exactly comes down to these sort of coherent states.
Okay, thanks.
Any more questions, comments?
I have related to, sorry.
Go ahead, Sachiko.
Sorry, I have related question with Sabas. So the application of the last slide application to machine learning. So do you have you said that you didn't compare with classical method, but apart from computation time, what do you expect that the quantum computing can improve something?
Good, yeah. So there's a couple. I mean, there's the things that I would expect would be that it would sort of improve the time, and also potentially just include sort of how many parameters we can do, right? I mean, because I mean, essentially, the number of qubits really has to do with sort of the number of parameters that we're sort of scanning over. So, if we can have more of those, that might be useful. But yeah, I mean, I think for these applications, it really is the runtime, which it's that, and also if we can sort of start using similar things for different processes and sort of having, sort of generate from scratch the classical data set, if we can do something to sort of not have to do all of that work, I think is important. So it's both computational runtime and also human labor time.
Oh, okay. Thank you.
Shall I? Yeah.
Yes, please.
Hi. Thanks for the talk. I wanted to ask concerning the status of non-Abelian simulations.
Good.
What's the status? How are we doing there? Is
Good.
there progress or?
Yeah, I think we are. So I currently don't have any work on the non-Abelian side, though Krish and I are definitely thinking hard about whether we can do sort of something similar for non-Abelian. I think on the non-Abelian side, there has been a lot of interesting ideas. There's been a lot of proposal about how to do this. People have really been thinking hard about how to digitize non-Abelian theories. I think there hasn't been one clear winner in all of this. So there's many ideas, but it's just not clear what is the best way. And I think, I mean, even, and this is something, that we have to be very honest about, so here I say, well, we only need 7 states per site. That's great, if I can do this on a classical computer, but now on a quantum computer, it's not the only thing. Let me start that sentence over. On a quantum computer, it's not only the number of qubits that's important, but also how many operations I have in my circuit. So, if it turns out that this requires an absurd number of gates, then that's a hard issue for current, non-error corrected quantum computers. And so I think, with non-Abelian theories, my sort of current understanding of the field, which could be inaccurate, is that there is a lot of theoretical developments of here's how we could do it, but not as many here's the actual gate count and qubit count, and here's how it would actually look on a quantum computer.
Mm-hmm. Okay.
Yeah, that's so I think, yeah, non-Abelian is still, I mean, even Abelian is still very much an open question about how it actually behaves on a quantum computer when you start looking at larger systems.
Okay, thanks.
Okay, any more questions, comments from the audience? Okay, I have one last question.
Yeah.
So traditional computers emit about 2 tons of CO2 carbon dioxide per million CPU hour. So is there any similar benchmark for quantum computers? Do you know how much CO2 they emit?
Yeah, very good question. So this is one of the things that we actually talk a lot about in our sort of private collaboration meetings. And I don't know off the top of my head, but if I recall, there is a statement that in general, the sort of like electric needs, which is not the same as CO2, but we can correlate them, are generally lower for quantum computers. And so this is actually sort of one of the things that I was like, I'm not quite sure if I want to mention this for the quantum machine learning, because it's not something that we have actively looked at. And I don't quite know how to quantify it yet. But yes, if it turns out that, even if the run times are similar, but your, energy needs are significantly lower with a quantum computer, that actually might be more important. It's not as important for, encryption breaking. But for humans living in a world suffering from global warming,
exactly.
Probably something we should consider.
Yes. Okay. If there are no more questions, then I think we can thank the speaker again. Thank you again for this very nice talk.
Thank you.
It was a pleasure.